In this video, we're going to go through the second section in the opening chapter of the trigonometry textbook. And this is still going to be a review of some concepts from geometry that the text feels would be good for us to review before we actually start trigonometry, which we're going to do in the next section. But in this video, we're going to talk about angle relationships and similar triangles. So again, everything we're about to talk about in this section are concepts we go through in detail in geometry. I plan to do a geometry playlist, a full course. So depending on when you're watching this video, that course might already be posted if you want to go take a look at some of those videos. But okay, in figure 13 here, we extended the sides of angle NMP to form another angle RMQ. So angle NMP, they had this as an angle, but then they extended the sides. So now you've got these two lines, not line segments or rays, these two lines that cross each other. And what happens is you have this angle NMP and QMR are what are called vertical angles. And vertical angles are equal. They have equal measures. But you can see that in extending these lines, another pair of vertical angles formed, this NMQ and RMP. And those angles are equal. Now, these four angles as a unit aren't equal. Only the vertical angles are equal. But like NMQ and QMR, we can see are supplementary. They add to 180, right? And same idea with NMP and PMR. So you could relate, these are all kind of related to each other. These two are equal, but then these two are these two are supplementary. So vertical angles have equal measures. All right, parallel lines are lines that lie in the same plane and do not intersect. And so, like we talked about in the previous section, everything that we do that we're doing in this entire course, we're just thinking about everything in a single plane. But just remember that you can think about the idea of, so here's like three-dimensional space, and you can have any plane in 3D space. It could be along, like, here's like the X, or this would be the the ZY plane, or here's the XY plane. Here's the XZ plane, but you can have planes oriented anywhere. And so you can imagine, just think about that, how everything that we're doing, kind of think about that you could be doing this in any plane in 3D space, right? There's an infinite number of planes in all of 3D space that you could pick out. So just think about, like, you could think about all these concepts we can think about in any plane, not just like, we're not living in a 2D world. You can think about this in any plane. Again, parallel lines, they lie in the same plane and do not intersect. So according to this definition, just to point this out, you might find this interesting. If we come to 3D, you could have two lines in 3D could never intersect, but they don't lie in the same plane, right? So according to this definition, those lines technically aren't parallel. They need to be in the same plane and not intersect. Right? You can't draw, if this line's kind of going into the page and to the right, this line's going like up and out of the page, but if you extend this, they technically would never intersect, but like, would you call those parallel? Well, according to this definition, those aren't parallel, even though they don't intersect. They need to be in the same plane. Figure 14 shows parallel lines M and N. When a line Q intersects two parallel lines, Q is called a transversal. So a line that intersects two parallel lines is called a transversal. In figure 14, the transversal intersecting the parallel lines forms 8 angles indicated by numbers. Right? So you got two parallel lines which are in a plane, right? And a line that's be any line that's not parallel to those two lines is going to intersect those two lines, and that intersecting line is called a transversal. and it forms 8 angles. We learn in geometry that the degree measures of angles 1 through 8 in figure 14 possess some special properties. The following table gives the names of these angles and rules about their measures. So yeah, you should be familiar with this. So you have alternate interior angles are going to be equal. Alternate exterior angles are going to be equal. The interior angles on the same side of the transversal add to 180. And then corresponding angles, so like these types of angles, are equal. And you can think about it, they figured this out because you have vertical angles here. So if opposite interior angles are equal, then these two angles are going to be equal as well. Okay, so you should be really familiar with this, with angles in relation to a transversal cutting across two parallel lines. You should be really familiar with all this. But we'll still work a bunch of examples. Find the measures of angles 1, 2, 3, and 4 in figure 15, given that lines M and N are parallel. So M and N are parallel, and they're cut by this transversal line. So, okay, how are these two related? Well, these are alternate exterior angles, right? So we can set these equal. You've got 3x plus 2 is equal to 5x minus 40. So 5x minus 3x is 2x. And then minus 40 plus 2 is 42. So x is equal to 21. So 21 times 3 is 63. 63 plus 2 is 65 degrees. So this angle is 65, and this angle is 65. All right, okay, well, that's 1 and 4. So what about 2 and 3? Well, we can see that 3 is going to be 65, right? These two are vertical angles. And then angle 2, I mean, we could, kind of go through these properties, but we can just see angle 2 is supplementary to angle 1. So what is 180 minus 65? $115. Okay. An important property of triangles, first proved by Greek geometers, deals with the sum of the measures of the angles of any triangle. So yeah, the sum of the measures of the angles of any triangle is 180 degrees. And they give an argument for this, but so you should obviously know this. Okay, so here they use the angle sum to find x. So this could be x is going to be 180 minus 48 minus 61. Very easy stuff. Types of triangles. So an acute triangle means that all of the interior angles are acute. We just call those the interior angles, the angles of the triangle. A right triangle has one right angle, one 90-degree angle. An obtuse triangle has one obtuse angle. You can't have more than one obtuse angle in a triangle. Okay, so all acute angles is an acute triangle. One right angle is a right triangle. And then one obtuse angle is an obtuse triangle. Okay, with an equilateral triangle, all side lengths are equal. An isosceles triangle, two side lengths are equal. And then a scalene triangle, you have no sides equal. All right, similar triangles are triangles of exactly the same shape, but not necessarily the same size. So they have the exact same shape, but not the same size. Or they could have the same size, and that's like if you have two triangles that are the exact same triangle, then they're congruent and similar, but that's kind of like a trivial case. But in general, if you have two triangles that aren't the same, but they're similar, then they have not the same size, but the same shape. And the way you think about having the same shape is that they have the same angles, like the corresponding angles are the same. Okay, figure 18 in the next page shows three pairs of similar triangles. The two triangles in figure 18C have not only the same shape, but the same size. Triangles that are both the same size and the same shape are congruent triangles. If two triangles are congruent, then it is possible to pick one of them up and place them on top of the other so that they coincide. All right, so yeah, all of these are similar, but these are the exact same triangles. They're congruent. These are not the same size, but they're similar. And so the idea is you look at like the corresponding angles are going to be the same. That's what the same shape means, right? Corresponding angles are the same. If two triangles are congruent, then they must be similar. However, two similar triangles need not be congruent. Yeah, look, these triangles aren't congruent, but they're similar. But if you have two congruent triangles, then of course they're similar. Again, that's like the trivial case. The triangular supports for a child's swing set are congruent and thus similar triangles, machine produced with exactly the same dimensions each time. These supports are just one example of similar triangles. The supports of a long bridge, all the same shape but increasing in size towards the center of the bridge, are examples of similar but not congruent figures. Yeah, so it's like these are the same exact shape, these triangles here for these supports, but the supports increase in size towards the center of the bridge. Consider the correspondence between triangles ABC and DEF. So yeah, they just talk about how the corresponding angles are the same when it comes to a similar triangle or similar triangles, right? B corresponds to E, those angles are the same. A corresponds to D, those angles are the same. C corresponds to F, those angles are the same. But all these angles are different though. Like it's not like B has to be equal to C or anything like that. All right, conditions for similar triangles. So triangle ABC is similar to triangle DEF, so we're looking here. But this is just a general case, right? If the following conditions hold. So the corresponding angles have the same measure. That means they're similar. But then also, what's also going to happen with similar triangles is the corresponding sides are going to be proportional. That is, the ratios of their corresponding sides are equal. So that's another thing that makes the shapes the same. It's not just the angles, but it's also, I think it's the case that if it's not like you can have two triangles where the corresponding angles are the same, but they're not similar. I think once the corresponding angles are the same, then it's similar. And so, like, you can't have corresponding angles be the same, but then the sides not be equally proportional. Okay, so, but what that means is that, like, if you take the length of AB and divide that by DE, you're going to get a ratio, a number. That number is going to be the same as, like the length of BC divided by EF is going to be that same number, and the length of AC divided by DF is going to be that same number. That's a property of similar triangles, in addition to the corresponding angles being the same. All right, in Figure 20, triangles ABC and MP are similar. Find all unknown angle measures. So, okay, you have 45 and 45. This is 104. That means angle C is going to be 104. And then you can do 180 minus 45 minus 104 to get angle B, and then B is going to be equal to M. And in the next video, we'll work example problems so you can get a better feel for problems like this. Finding side lengths in similar triangles. Given that triangle ABC and triangle DFE in Figure 21 are similar, find the lengths of the unknown sides of triangle DE or DFE. So what you do is, these AC, that's the line between these two angles. DE and AC are like the corresponding sides, and if you take 16 divided by 8, you get 2. So that means that, like, CE, the side between these two angles, divided by EF is also going to be 2. So what is 32 divided by 2? That's 16. Okay, the 24, the length of AB divided by this corresponding side is going to also be 2. So what's 24 divided by 2? That's 12. Okay, so again, we're going to work example problems and go through this more slowly, problems like this. All right, finding the height of a flagpole. They're just kind of giving a more real-life example. Workers must measure the height of a building flagpole. They find that at the instant when the shadow of the building is 18 meters long, the shadow of the flagpole is 27 meters long. The building is 10 meters high. Find the height of the flagpole. So based on the shadow, you can conclude that the triangles are similar, right? Because like the orientation of the sun to the building and the flagpole is going to be exactly the same. So the sun's rays are coming into the exact same angle. So you can assume that the two triangles are the exact same shape, but not necessarily the same size. And so you know the length of the shadow of each. So you could say, so 27 divided by 18, okay, that's going to be equal to, you take the height of the flagpole, which you don't know, and divide that by the height of the building. Okay, so cross multiply, you've got 18x is equal to 210. Divide both sides by 18. 270 divided by 18 is 15. So you can estimate that the flagpole is 15 meters high. Okay, so now we're going to work some more example problems in the next video.